In section 6.4, we're going to work on defining radians, talking about arc length and angular speed. So our objectives are to find points on the unit circle determined by real numbers, convert between radian measure and degree measure, find coterminal, complementary, and supplementary angles in both radian and degree measure, and then find the length of an arc in a circle, and then measure the central angle of a circle. And then finally, convert between linear speed and angular speed. Quick review of circles. What do we know about the geometry of circles? Well, we're going to start with taking a look at a circle as positioned on an XY grid right here. So we've got X and Y. And I've attempted to draw a circle here. And I've drawn this circle here centered at the origin. So 0, 0 is its center. And the center at the origin is going to have a radius here of r. Now, if the center is at the origin, I can imagine a triangle formed here that's going to have x coordinate and y coordinate. And so the equation for this circle is going to be based off of the Pythagorean theorem, x squared plus y squared equals r squared. Now we can move our circle if we choose and give it some other point for its center. And this point right here, I'm going to call h, k for the center. And this circle is still going to have radius r. If I consider making a similar diagram for a triangle here that has radius r, the x value on the x-axis, this being the full x value, and the y value for this particular triangle, if this is x and this distance here is h, then the distance between the center and the edge of the triangle, remember x is this full distance over here, would be x minus h. And then similarly, if this distance here is k and this full distance is y, this side would be y minus k. So according to the Pythagorean theorem, the equation for this triangle would be x minus h, since that's the distance across the bottom of the triangle, squared, plus y minus k squared, that's this leg of the triangle, and again equals r squared. So it shows a little bit about what we know about the geometry of circles, and comes down here to that general form for the equation of a circle. As we can see right here, it's like we said, x minus h squared plus y minus k squared equals r squared for a circle with radius r and a center point at h, k. So those are just some general things about circles, and they're really built off of the Pythagorean theorem, the equation for a circle here. Now, that's generally about circles. The circle that we are going to talk about in particular in this section is going to be the unit circle. And the unit circle is going to have its center at the origin, and it's going to have a radius value of 1. So its center is going to be 0, 0, and its radius is going to be 1. So if you put those together with the equation for a circle, if it's centered at 0, 0, h and k are both 0, so x minus h and y minus k turn back into x squared plus y squared. And the radius is 1, so when we're equal to r squared, 1 squared is 1. So the equation for the unit circle is going to be x squared plus y squared equals 1. We talk about the unit circle because it is the simplest circle. Its centers at the origin, and 1 is a very nice radius. It's a small whole number. The smallest whole number we could devise for the radius makes it the simplest equation of a circle. So that's why we're working with the unit circle right here. It's a basic circle. Now, we want to imagine that we have a point on the unit circle and we're going to move it around. So how far around will we move if we go one full cycle? So if you take your point and move it around the circle, the distance that that point travels in terms of circumference of this circle, think about the formula for circumference. The circumference of a circle is going to be 2 pi r. And so since r is equal to 1, if you go all the way around the circle one time, you've gone 2 pi in distance. So if I go one full cycle, I've traveled a distance around this circle's edge of 2 pi. If you go 2 full cycles, you go 2 pi and 2 more pi. That would be a distance of 4 pi. And if you go half of a cycle, you would go only 1 pi. 2 pi all the way around, you would go 2 pi divided by 2. You'd go a distance of pi around the edge of that circle. What if we went 1/4 of the way around? 2 pi divided by 4 would be a distance of pi over 2. So if I went 1/4 away around up to this area, I would have gone a distance of pi over 2. If I would have went 3/16, that's 3/16 times 2 pi. I can reduce that. 2 goes into 16 8 times. So my full distance traveled would be 3 pi over 8. It doesn't matter what fraction it is. I can calculate the distance I've traveled in the same way. 4/3 of 2 pi be 2 pi times 4/3, or 8 pi thirds. Okay. Next page. In general, a point traveling around the unit circle covers how much distance per revolution? So it's going to cover 2 pi distance times the number of revolutions. Covers a distance of 2 pi times the number of revolutions. That's what we were doing on the previous page. 2 pi for one full revolution. 2 pi times 2 or 4 pi for 2 revolutions, or times 1/4 for 1/4 of a revolution, and so on. As usual, we want to be as thorough and precise as possible, so we'll measure distances around the unit circle starting from a point of 1, 0, or where the circle crosses the x-axis right here at that angle 0 degrees. And we want to label the distances traveled by each point. So if I look at these markers right here, remember that it was pi to go half a revolution and 2 pi to go a full revolution. So I have 1, 2, 3, 4, 5, 6. So these markers are each the size of a 1/6 as the fraction. Since there are 6 of them, 1, 2, 3, 4, 5, 6 in a single pi fraction. So this is 1/6 pi as one revolution. So 1, 2, 3, 4, 5, 6. Remember, 6 pi sixths would reduce back to 1 pi. 7/6, 8/6, 9/6, 10/6. So this location right here would be a rotation of 10 pi over 6, which would reduce then to 5 pi over 3. So that distance traveled to go around the circle until this marker would be a distance traveled of 5 pi over 6. Okay. All right, this next one, I want to travel all the way around the circle and then up another quarter rotation. So I remember that this is pi again. 2 pi is a complete circle. And so if it's starting at 0, then you don't move at all. If that's pi, this has to be half of pi. So what I have here is this full rotation, which is 2 pi, plus this quarter rotation, which is a half of pi, pi over 2. So the full distance is going to be, for this angle, 2 pi plus pi over 2. So 2 pi, that's 4 pi over 2. We're just getting a common denominator. Plus pi over 2 would be the distance 5 pi over 2. Okay, let's look at another one over here. It looks like we've got 2 whole revolutions one whole revolution and then half and a little bit more right here. Got to make an assumption that this marker is about the same size as this marker right here because I don't have enough to be able to count how equally spaced they are. But I've got, this is a distance of 2 pi to do that full first rotation. Then this would be an additional distance of a single pi. And then this last little bit right here would be one of these sixths, right? We counted 1 6, 2 6, 3 6. That's about a marker of an additional 1/6 of pi. So that's going to be another pi over 6. So 2 pi plus pi over 6 would be that complete distance. So that's a measure of 3 pi plus pi over 6. 3 times 6, 3 pi is 18 pi over 6 plus pi over 6 would be a measure of, oops, I need to write 19 here, would be a measure of 19 pi over 6. Okay, so we're able to find the distances around the unit circle. Again, the arcs were spaced out just to show us if they lied on top of each other, I might not know that I was rotating around once or twice or 3 times. But a full rotation is 2 pi plus another half rotation is a pi. And about pi 6, just again, each of these being 1/6, and that appears to be the same size as this. Okay. All right. Note, we can think about angular measurement in terms of the distance around the unit circle. Okay. So we can think about our angular measurement here in terms of distance around the unit circle. And that's going to be what radian measure does for us. So far, we've made use of degrees as a unit of an angle measurement, but degrees are just as arbitrary as grails, mids, turns, hours, feet. They're an arbitrary measurement that was decided upon hundreds of years ago. But we can be a little more scientific and precise about this if we come up with a way of measuring angles that is not arbitrary. The size of 1 degree was decided by some old dead person, but the measurement in terms of distance around the unit circle, that's based on a formula. It's not arbitrary. It's based on the circumference of that circle. Okay, so imagine an arc length of exactly 1 along the unit circle. The arc length is exactly the length of the radius in this case. So the arc length is 1. The arc length is equal to the radius in this case. This occurs at the precise angle that is referred to as 1 radian. Now, 1 radian is going to be when the arc length on that circle is equal to 1 as the radius here. Radians are measured in terms of their relationship to the circumference of the circle, but a measure of 1 degree is very arbitrarily this tiny little measurement right here, and 1 radian is approximately 57.3 degrees. So there's not a good way of figuring out degrees in terms of arc length. Radius degrees are a much more arbitrary measure. However, there is certainly a relationship between them. How many radians are there in 1 360-degree full circle? That was our full circumference. So that was 2 pi radians were equal to 360 degrees. That came from our full circumference. Okay. On to the next page. So I can convert between degree measure and radian measure. Now I know that 2 pi is equal to 360 degrees, but there's no need to multiply by that additional 2. So if I divide both sides of the equation by 2, it means that pi is equal to 180 degrees. So I just divide by 2 on both sides. So that's going to be a little more convenient to work with than 2 pi for 360. So if we're going to convert between degree measure and radian measure, we can use pi radians over 180 degrees, or vice versa, 180 degrees over pi radians, depending on if I'm converting from degrees to radians or radians to degrees. To go from degrees to radians, we'll need to multiply by the pi radians over the 180 degrees, but to go from radians to degrees, we would do the reverse, multiply by 180 over pi radians. Okay, so let's look at a couple of these. One of the other notes about this is that we typically like to keep our radian measure in terms of pi instead of using a decimal measure. That will keep it more exact. We don't multiply the pi out, we leave pi as a symbol pi. So for the most part, we do not expand the value of pi. When converting into radian measure. So we are going to convert our angles from degrees into radians or vice versa. Another important note right here is that any angle stated without accompanying units is presumed to be measured in radians. So if the angle is in degrees, the degree symbol must be listed. Radians are unitless. There's no symbol needed for radians. So if I put no symbol next to something, we're going to assume that the measure is in radians, not degrees. Degrees have to have the degree symbol. Okay, so let me get a calculator. I'm going to clear this one here. And we're going to convert 135 degrees into radians. So I'm going to multiply this by pi radians over 180 degrees. On the calculator, I'm going to be typing in the 135 degrees divided by the 180 degrees, I'm not going to type the pi. I'm going to save that for the by hand portion so I can leave it in terms of pi. So 135 times, we'll do just 1 over 180, or you could do 135 divided by 180. I am going to use fraction form wherever possible. So this reduces to the fraction 3/4 of pi, or 3 pi over 4. So 3 pi over 4 is the simplified version of this angle in radian measure. Let's look at another one. This one's negative 30 degrees times pi over 180 degrees. We'll use a similar technique. We're going to take negative 30 times 1 over 180, convert this into a fraction, negative 1/6. So we're going to have negative 1 pi, or negative pi, over 6. That is our simplified angle in radian measure. All right, now when I convert something that's already in radian measure, negative 3 pi over 4, into degrees, we're going to take negative 3 pi over 4 times the 180 degrees on top, pi on the bottom. Again, I don't need to type pi into my calculation because the pi fractions will cancel there. And I can simply multiply the negative 3/4 by the 180. And that's going to come out as negative 135 degrees. For pi ninths, let's work this one similarly. We have pi ninths times 180 degrees over pi radians. We multiply these, and we know that the pi's are going to cancel. That's the reason for putting the radians in the denominator, to get that to simplify and to give me a final answer in degrees. So I've got 1/9 from that first fraction times the 180 over 1 from the second fraction, comes out as 20 degrees. Okay. And the last two, negative 6 pi, that's in radians. So negative 6 pi times 180 degrees over pi. This is going to, again, reduce the pi's out and give me negative 6 times 180 degrees. That's negative 1,080 degrees. And then finally, 25. This is not 25 degrees because there's no degree symbol. This is 25 in radians. So I need to convert this into degrees by multiplying by 180 degrees over pi radians. This is a time that I'm actually going to need to divide by pi, since the degree measurements are not supposed to be in terms of pi. So we are going to multiply that out and get something that's a kind of messy decimal from our 25 times 180 divided by pi. So this is approximately 1,432.4 degrees. One of the things that I notice here is that working in radian measure does allow me to use values that are a lot smaller than working in degree measure. Something like 1,080 degrees is only 6 pi, or negative 6 pi right here. So the numbers are a bit more convenient when they're written in radian measure. It's going to be one of the reasons we're going to want to use radian measure in the future. Okay. Now, the special angles are shown down below. Note that the angle 0 degrees also corresponds with the angle 0 in radians, as well as the angle 2 pi in radians, or 360 degrees in degrees. We saw some of these earlier, but not all of them. The angle pi sixths corresponds with 30 degrees. It's one of our special angles, 30 degrees. So pi sixths is also a special angle in radian measure. We know that 45 degrees is a special angle, so its corresponding radian measure, pi fourths, is also a special angle. 60 degrees corresponds with the radian measure, pi thirds. And then our axes, 90 degrees corresponds with pi halves, 180 corresponds with pi, 3 pi halves corresponds with 270, and we've already mentioned the 0 and the 2 pi for the positive x-axis. So these are the primary set of special angles. We can also talk about corresponding special angles in other coordinates, other quadrants. So we could talk about 3 pi fourths, which is the pi fourths angle referenced in the second quadrant. It's 135 degrees, or 3 pi fourths. And then similarly, we can talk about the angles that have reference angles to 45 degrees in the other quadrants. And we can do the same thing for the 30s and the 60s as well. This diagram doesn't contain those, but we will see those on future diagrams. The angles in this diagram are all in their positive rotation. And then the angles over here are all similar, but in the negative rotation. So as you can see, this information shows the same thing, but we've now labeled the angles going in the opposite direction. We do focus on the positive rotation, but we can always write coterminal angles in either orientation. Okay, note at the bottom is we should definitely memorize the reference angles for our special angles in both radians and degrees. We'll be working on memorizing those throughout this chapter. Okay, next topic, we've got ourselves arc length and central angles. A degree is exactly the same size regardless of the size of the circle it's in. And that does also need to be true for radians. But the consequence is that because the radius can change, that does change the circumference, we need to talk about discussing the arc length versus the radian measure. So radians can be used to measure angles in any size of circle, not just a circle whose radius is 1, aka the unit circle. So we are going to look at the same angle in two circles with different radii. These radii are called S and S1 right here, or the S and S1 are the arc lengths. I'm just reading this a little bit better here. These two radii here are 1. So this first circle is the unit circle, and then R, the second circle, has some larger radius. Okay, so one of these radius is 1 is not. S is the symbol for arc length. I'm not sure why the letter S got chosen for that, but it is. So S is the symbol that we would use for arc length. And in the first diagram, because the radius is 1, this arc length S1 is going to be equal to the radian measure. So on the unit circle, which has radius 1, arc length equals radian measure. So that happens in that pink circle right here. That is the radian measure S1. On the other circle, on any other circle, the arc length to radius ratios are going to be the same. So that means that the arc length, which is S, the ratio of S to R, is going to be equal to the ratio of S1 to 1, which means that if I multiply both sides by R, S is equal to R times S1. Now, I'm going to rephrase that again one more time because the arc length is equal to the radian measure. So let's call that S1 equal to the angle theta. Typically, we do use the Greek letters for theta. This is going to be my angle theta. So in any other circle, S is equal to R times theta. That's how I would like to see this right here. So in any other circle, arc length is equal to radius times angular measure. So arc length, I'm just going to write this in words, equals radius times radian measure. That's what we said here. And I believe that's what's said here below. Provided we use radians as our measurement for the angle, we can devise the sine of the angle in radians as a ratio of the arc to radius. That's what we have done here. Okay, so let's look at an example of doing this. So we're going to compute this table so that each row relates the angle, the radius, and the arc length. If my arc length is a distance of 200 centimeters and my angle is 45 degrees, I need to convert this 45 degrees into radian measure because I must be in radian measure in order to work in terms of arc length here. So I'm going to multiply by pi over 180 degrees. And I would, if I finished that computation, come out with a radian angle of pi fourths. Okay. Now, the arc length, S, is equal to radius times radian measure. So I have here that 200 is equal to R times pi fourths. So it means that my R, multiply the 4 over, that's 800, divide off the pi. R is a measure of 800 divided by pi. Okay. Let's look at another example. In this one, I know the radius and I know the angle. That angle is given to me in radian measure. So to find the arc length, I need to take R, 4.2, times the 5 pi 12ths. Typically, as we multiply these, we don't type in the pi, we keep pi itself. So I'll take 4.2 times 5 12ths, and that comes out as 7/4 or 1.75 times pi. So the arc length is 7 pi over 4, or 1.75 pi. We use fractions a lot in terms of radians, so I'm going to keep it as the fraction. In the last one here, we know that S, which is 8, is equal to R, 3.5, times our angle. So if I take 8 and divide it by 3.5, that's going to give us a radian measure of 16 sevenths. Okay. All right, so this printed a little funny. This should be on the next page. Let me get my second page here ready. Here we go. Topic 4, linear speed and angular speed. We're very familiar with the basic formula for determining the average speed of an object. So you might know, just thinking about the relationship between distance and speed, that distance is equal to rate times time, and speed is just the absolute value of rate. So when we're talking about rate, we're talking about speed, as long as we're considering positives for the rate there. So if we want to find the average speed of an object, we could divide by t and say that rate is equal to distance divided by time. And we should be pretty familiar with that formula when we talk about speed. They're measurements of distance divided by time, like miles divided by hours, miles per hour, or feet per second. They're always distance units divided by time units to talk about speed. Okay. But this is linear speed. And that is speed that's moving along a straight line path. So this formula right here is a formula for linear speed, speed along a straight line path. Similarly, we can measure the average rotational speed by considering angles and time. So instead of a straight line distance, we'll consider angular distance with time. In my diagram here, we're going to think about a particle on the edge of this arc that is being pulled along, and its straight line speed is going to be different from its angular rotational speed right here. I do need to relabel this right here. The word R is used for rate. I noticed down here we're using V for velocity, so I'm going to also write this as V equals d over t. It's just a synonym. We can use R for rate or velocity. Lots of words that can be used for that particular word. V for velocity, same thing as R for rate, just a different paraphrasing of that formula. Okay, so putting this together with this idea of that arc length right here, we have arc length, which is S equals R times theta. If we made this into a speed by dividing both sides by time, recall that S is a distance measurement, right? Arc length is a distance. So what I have on this side by doing S divided by T is the same as distance divided by time. So this is a measure of velocity. So velocity or speed is equal to R times theta divided by T. And in this case, we're going to call that theta divided by T our angular speed. The symbol that we use for angular speed is omega. So it looks a little bit like a W, but it is an omega. It's the Greek letter omega. Oh. And omega is going to be defined to be theta divided by T. Okay, so in conclusion here, we've got this box that says that if I want to talk about linear speed, v, of a point that is a distance r from the center of the rotation is given by v equals r times omega. We're subbing in omega right here. V equals R times omega, where omega is the angular speed, and angular speed is measured in radians for the angle per unit of time. So a couple different formulas. For linear speed, we can have V equals distance divided by time, and we can have V equals R omega. And for angular speed, just recapping here, for angular speed, we could have omega equals theta divided by t, depending what you had. Or if you solve this formula for omega, it's also equal to linear speed divided by r. So different ways of paraphrasing and rewriting those formulas in terms of different variables. Okay, so let's take a look at a couple of examples here. We have a water wheel. So this is something like an old-fashioned mill might have. A water wheel has a 4-meter radius, and it turns due to flow of a river. After watching the wheel, you notice that it makes about 8 full revolutions in 1 minute. My goal is to estimate the linear speed of the river. First, to get the linear speed of the river, I'm going to need to figure out the angular speed. So let's see if we can get that angular speed first. Okay. It makes about 8 full revolutions in 1 minute. So the angular speed is going to be the angular measure, the radian measure, divided by the amount of time. So 8 revolutions, 8 full revolutions, 1 revolution being a matter of 2 pi in radians. So that's 8 revolutions of 2 pi radians each in 1 minute. So angular speed is 16 pi radians per minute. Remember that I don't have to write a unit for radian. 16 pi with no unit is in radians, and this is per minute. That's going to be our angular speed, and my goal is to find the linear speed. So the linear speed is going to be equal to the radius times the angular speed. We've got a 4-meter radius times 16 pi radians per minute in angular speed. And that's going to come out as 4 times 16 is 64. So 64 pi meters per minute. And again, in terms of speed, we would technically multiply that pi out, because if you ask how fast something is, 64 pi meters per minute is not comparable to a flat decimal value. So let's go multiply 64 times pi. This is the speed of 201 meters per minute. And you could convert that to other units if needed, convert to miles per hour or meters per second, depending on what you want to compare this with. But we're going to leave this right now in the units the problem had started out with, in meters and minutes. If the water wheel keeps spinning at this rate, and it would with a constant flow of water, how many days would it take for it to rotate 1 million times? Okay. Here I'm looking for the number of days it takes to make a rotation of 1 million rotations. So I'm not working from linear speed right here, since linear speed is about flat line distance, not rotational distance. So what I know about this is that it rotates 8 full revolutions in 1 minute. So we're going to go back to that information that we have 8 revolutions per 1 minute. And we're going to try to figure out how many minutes or days what it's going to take in order to get 1 million revolutions. Okay. To rotate 1 million times, that is 1 million. Revolutions. We know if we convert that 1 revolution is a measure of 2 pi radians. We did that conversion up here as well. So if I multiply by 2 pi, I'm going to convert from revolutions into radians. And I know that if I use, I actually don't need to use this right here since I've already used it up here. I can convert the angular speed and say that the angular, there's multiple ways to do this. I just went this way first. So the radian measure right here was 16 pi per minute. I might go back and do this one a second time because I think I thought of an easier way, but we're going to keep going on this one right here. Converting out of radian measure into minutes. And then I need to do minutes into hours. So 60 minutes is in 1 hour. And days is my eventual goal. So 24-hour, 1 day. And that would convert us into our goal units, how many days. So just a little bit of unit conversion. Let's get this multiplication going. I need to do the 1 million times 2 pi times 1 over 16 pi times the 1 over 60, and then finally times the 1 over 24 would come out as about 86.8 days. All right, so just a real quick recap. I was saying thought I was going to use this 8 revs per minute, and I could have. It would have worked out the same way. Let me take the 1 million, and that is in revolutions. So if I had multiplied that, instead of going down to radians and then back to minutes, I could have converted with this one conversion instead of these 2. I wasn't thinking straight. So if I did this one, it would be a multiplier of 1 over 8, which this fraction does reduce to. Again, times the 1 over 60 times the 1 over 24. So again, same thing. When my brain started this one, I was just working on converting into radians. Not sure why. So trying to explain my other path right here could have been to use this in place of those 2 things, right? Using the 8 revolutions on the bottom per 1 minute on the top. Alternate path to the same thing, both give us the correct answer. All right. Let's take a look at our next page. Let me shrink Desmos. All right, and our next and last page here. An SUV has tires that have a 17-inch radius. If the SUV rolls forward 4 feet, what is the angle of rotation for the tires? Make a diagram. So I've got my tire, and it has a radius of 17 inches. And if it rolls, so it's like rolling down for 4 feet, this 4 feet that it's going to travel is going to be its total arc length once it spins all the way around. Let's convert that into inches. So 4 feet would be 48 inches. And if I want to know the angle of rotation, I know that S, arc length, is equal to R, radius, times angle in radian measure. So I'm trying to figure out what theta is after knowing that the radius is 17 and the arc length is 48. So 48 equals 17 theta. I'm going to divide both sides by 17. Theta is equal to 48/17, or approximately, let's find out, 48/17 is an angle of approximately 2.82 radians. If we need to use this number again in the next piece, we'll of course use the exact value of 48/17 radians. All right, if the tire rotates 35 times, how much distance has the SUV traveled horizontally? Okay, if it's going to rotate 35 times, I think I'm still using the S equals R theta formula. But instead of rotating just the 48/17 time, which is to travel a distance of 4 feet, I'm going to have a different angle, and that angle is going to be comprised of a full 35 rotations. So the angle is going to be 35 revolutions times 2 pi radians per revolution. So that's going to be a measure of 70 pi for the angle. And the radius is still 17 inches. So the distance traveled, the arc length here, is going to be 17 inches times 70 pi in radians. 17 times 70 pi is going to come out as 3,738.5 inches, or we can convert 12 feet to an inch. We can divide this by 12 and say that it's traveled about 311.5 feet. I converted that one to feet because the original distance in part A was in feet, so we might as well answer a distance in part B in feet as well. Okay, final example here, number 7, says the Earth is roughly a sphere with a radius of about 4,000 miles, which rotates about once every 24 hours. What is the linear speed in miles per hour of a person standing on the equator due to this rotation? And then what about someone in Jackson, which is about 42 degrees north of the equator? All right, so in the first case, we wanted to know the linear speed of someone standing at the equator. We know the radius. So on the equator, I want to find the linear speed. So the linear speed is equal to R times omega. And I know R is going to be about 4,000 miles if I'm at the equator. If we are rotating about once every 24 hours, then omega is going to be, let's see, it takes one revolution, takes 24 hours, and there are 2 pi radians per revolution. So omega is going to be, if I reduce the 2 and the 24, it's going to be pi over 12th per hour, or 2 pi over 24 radians per hour comes down to pi 12ths if you reduce that fraction, radians per hour. So at the equator, the velocity is going to be about 4,000 miles times pi 12ths radians per hour. When I multiply these together, I am going to multiply the pi out because we want our speed in flat measurements, not in terms of pi. So that's 4,000 times pi over 12. Our speed comes out as approximately 1,047.2 miles per hour. Now, if you were not standing on the equator, where the radius was going to be 4,000 miles, if we're standing up higher at Jackson, Michigan, we are going to imagine a triangle here, where if this is the center of the Earth, then my radius out to the edge in any direction, whether it's out to this edge or out to this edge, is still 4,000 because the radius at any point on the sphere from the center is the same. And I know that I am about 42 degrees north of the equator. So I would measure that angle as how far north of the equator we are. That's 42 degrees is the angle of elevation. That's going to match the angle of depression. So my 42 degrees would be right on there in my triangle. And I need to figure out what the radius is at that point. So what is this value? So let's figure out this x value right here for this triangle. All right, so in terms of this triangle, it is a right triangle. The 90-degree angle would be there. So I would have the adjacent side and the hypotenuse side. So I'm going to use the cosine of the 42-degree angle. Cosine of 42 is equal to adjacent, which is what I've called x there, over the hypotenuse, which is the 4,000. Let's multiply the 4,000 to the other side. 4,000 times the cosine of 42 degrees is equal to x. Need a calculator for that. 4,000 times the cosine of 42. Let me make sure I'm in degree measure. I'm not sure that I am yet. Nope, I'm in radian measure, so let me switch that into degrees. That number should sound a little better. So we've got ourselves 2,972.58 for x. Okay, so now we are going to do a similar calculation for velocity. The radius has changed to 2,972.58 miles times that still 24 hours to rotate, so times that reduced fraction of pi 12ths radians per hour. I'm going to just copy this number, and we're going to multiply that by pi 12ths. And it's going to get us a number of 778.2 miles per hour. Having been to the equator, I can say that I don't feel the difference, or I didn't feel the difference in the linear speed due to lots of factors, but there was a physical difference in the speed from someone standing at the equator in terms of that linear speed. All right, that's the end of our section notes. See you again next time for the next section.